Here we have x as a random variable with the normal density function. Of 1 dividing by the square root of 2 pi times sigma times e to the negative 1/2 x minus mu over sigma squared. And once more, sigma is just a real number between 0 and infinity, and mu is just a real number. In earlier videos, we have shown that the integral from negative infinity to positive infinity with the normal density function as the integrand, we have shown that this is equal to 1. And for this video, see the description section for the video link. And we have also shown that the expected value of x, or the mean of x, the expected value of the random variable x, which is the integral from negative infinity to positive infinity, with the integrand x times this normal density function, and we have shown that this is equal to mu. So again, see the description section for the video link. And we have also shown in another video that the variant of x, which is the integral from negative infinity to positive infinity, of the with the integrand x minus mu squared times the normal density function, and we have shown that this is equal to sigma squared. Again, see the description section for the video link. And now we want to find what's called the moment generating function of x. And then we want to show how this moment generating function of x is related to mu into sigma squared. The moment generating function, defined as m of t, is the integral e to the t of x times the function f of x. And so in this case, we have e to the tx, where t is just a real number. T of x times 1 divided by the square root of 2 pi times sigma times e to the negative 1/2 x minus mu divided by sigma squared. So this is just e to the t of x times f of x, which is the normal density function. One over the square root of 2 pi times sigma. This is constant, so we can move this expression and place it in front of the integral. This is e to the tx, and this is e to the negative 1/2 times x minus mu over sigma squared. So we can rewrite this as e to the tx minus 1 over 2 sigma squared times x minus mu squared. This is x minus mu squared over sigma squared. So that's how we end up with 2 sigma squared. And now let's get the common denominator here. So we have this, the expression tx minus this. The common denominator is 2 sigma squared. So multiply tx by 2 sigma squared over 2 sigma squared. And now we have tx times 2 sigma squared minus all of this minus x squared. This is minus and this is minus, so it becomes plus, and this is minus times plus, so we have minus. And then the common denominator will be 2 sigma squared. And now let's rewrite the top here as this. With the negative here, put the negative in the front here, and then take the opposite of everything. Because we need to do what's called completing the square. So we put a minus here, then we take the opposite of each term on the top here. And so now we rearrange the terms. It'd be x squared. This term and this term, the common factors are minus 2x. So it'll be minus 2x times mu plus t times sigma squared. And then plus mu squared. And now we'll do completing the square in the exponent here. So here we have x squared minus 2x plus times mu plus t sigma squared plus mu squared. Half of this term here, the coefficient of x, half of negative 2 times mu plus t sigma squared. So we just multiply this expression here by 1/2. So multiply this expression by 1/2, then we end up with negative mu plus t sigma squared. And then square this quantity, and so we squared it. This is what we get. And so to this part here, we'll add mu plus t sigma square, and then minus the same thing. So adding this minus this is basically adding 0. So we're just completing the square. The first three terms here, the factors are x minus mu plus t squared sigma squared. So the first three terms here, these are the factors for the first three terms. And then we just write this as x minus mu plus t squared. And then this, if we expand it, we get minus mu squared minus 2 mu t sigma squared, and then minus t squared sigma to the 4th, and then plus mu squared. Minus mu squared plus mu squared is 0. So what's left is minus 2 mu sigma squared times t, minus sigma to the 4th times t squared. And therefore the top here becomes this. And then this exponent, we can write it as the first term here dividing by 2 sigma squared, and then the second term here dividing by 2 sigma squared. And notice we have a minus here in the front, so that makes this minus, and then here we have minus, minus. And so this minus will make this term becomes plus and plus. This integral is with respect to x. This term here, there's no x. And so as far as the integral is concerned, this term will be constant because there's no x here. So we can move it to the front and place it and move it and place it in front of the integral. And then here we end up with negative x minus mu plus t squared squared. We have shown in an earlier video that the integral from negative infinity to positive infinity with this normal density function here, this is equal to 1. And mu is just a real number. And so as long as mu is just a real number, then we get 1. But here we have the integral, this integral here. Instead of mu, so we can rewrite this right here. This is the same as this. Instead of mu, we just have mu plus t sigma squared. And so this is also equal to 1. And so it doesn't matter what this number is. As long as it's a real number, then this integral will equal to 1. And therefore, this integral right here, this is equal to 1. So this integral is equal to 1. And so the moment generating function is equal to this. And then times 1. And 2 mu sigma squared dividing by 2 sigma squared is just mu t. And mu, sigma to the 4th t squared divided by 2 sigma squared would be sigma squared t squared dividing by 2. And so for the normal density function, the moment generating function is equal to e to the mu t plus sigma squared t squared dividing by 2. And now we will see how this function is related to the expected value of x and the variance of x. So we have the moment generating function is equal to this. This is a function of t. And now we take the derivative here with with respect to t. The derivative of this expression with respect to t would be e to the mu t plus sigma squared t squared divided by 2. And then we have to use the chain rule. We have to multiply by the derivative with respect to t of the exponent expression. The derivative of mu t plus sigma squared t squared divided by 2 will be mu, and we're taking derivative with respect to t. So this will be sigma squared times 2t dividing by t, which is sigma squared t. So this is the first derivative with respect to t. Now let's do the second derivative. So the second derivative, we have a product. So this is a product. So it will be the first times the derivative of the second factor. So the derivative of this of mu plus sigma squared t is just sigma squared with respect to t. So it will be the first factor times the derivative of the second factor, and then plus the second factor times the derivative of the first factor. So the derivative of this is just this. We have just found the derivative of this, which is this whole thing right here. So that's what we have. And here, the common factors are sigma squared, or e to the mu t sigma squared, t squared divided by 2. So this is the common factor. And then what's not common is sigma squared plus, we can add one more step in here. And now we can see that the common factor is e to the mu t plus sigma squared, t squared divided by 2. And what's not common is sigma squared plus this expression squared. So this is the moment generating function of x, of the random variable x. This is the first derivative. This is the second derivative. And now let's evaluate the first derivative here at 0. So let t be 0. So we get 0. All of this will be 0. E to the 0 is just 1. And then here we get mu, so it's just mu. In an earlier video for the random variable x with the normal density function, mu is the expected value of x. And now let's look at the second derivative and let t be 0. So we have 0 here, and we have 0 here and 0 here. So all of this will be 0, and so here we get 1. What's left is sigma squared and mu squared. So for the moment generating function, the second derivative evaluating at 0 is sigma squared plus mu squared. And so the expected value of x will be the first derivative of the moment generating function. Evaluating at 0, we get mu. And then the variance of x will be the second derivative at 0 minus the first derivative at 0 squared. So this will be sigma squared. This right here, this is sigma squared plus mu squared, and then minus mu squared is equal to sigma squared. And so this shows how the expected value of x and the variance of x, how they related to the moment generating function.